Hello there. My name is Martin Freer. I'm a professor in the nuclear physics group here at the School of Physics and Astronomy, University of Birmingham. And what I'm going to tell you about are some of the things that interest me in terms of my own research, um, how that fits into the teaching that you will get here at the university, and indeed a rather deep question: how on earth we all got here, and what we are made of. It's captured in this first slide here, which you can see is a rather dramatic explosion in space, and flying out of it come some nuclei. And if we try and understand those processes, and indeed how the universe came to be as it is today, a good way of thinking about it is the following diagram. What you see is the beginning of time, Big Bang, a period of time called inflation. We transition through a quark soup, or more properly, a quark gluon plasma, get to a point where we condense out into protons and neutrons, and then the universe evolves as time goes by, and we end up with the stars and galaxies of the modern universe. And somewhere in that process are the elements from which we are composed of. These are constructed, and you might wonder, what is it we are made of? And if one was to write down a list of all of the elements and their relative amounts, masses, this is what you'll find. We're dominated, obviously, by oxygen, hydrogen from the large amount of water contained in our bodies, carbon, a lot of organic matter, but then one can work way down the list and you see iron, obviously, in the hemoglobin in the blood, but all sorts of other elements. Is that all? Well, if one keeps analyzing smaller and smaller components, you find that the list goes on. And in fact, some strange components. So arsenic, which normally one might think is toxic, that's inside our body, uh, and other elements. And one could keep going. And here is finally the complete list. And vanadium here is highlighted because it is the last functional element inside our bodies. As we go to thorium, uranium, they're inside our bodies but have no biological function. Everything else above determines how we function as biological objects. And change those balances, of course, change the way that we work. And if one was to try and analyze the composition of our bodies and look for a correspondence in the abundance of elements, there's a rather interesting correlation. What this shows is abundance relative to silicon. So logarithmic scale here, going up in orders of magnitude against mass number. And one sees that the light elements are most abundant, and then as you go to heavier elements, it decreases. And there are some heavier elements like this peak around lead and platinum, barium, and xenon, where there is enhanced abundance. Now, how all of these elements are made is a part of the subject of nuclear physics, and indeed a subdiscipline called nuclear astrophysics. And people spend their lives trying to understand what kinds of processes gave rise to these elements. And as you can see here, we have a periodic table which has been classified in terms of different types of scenarios. So we have Big Bang fusion. We'll come back to that. We have merging neutron stars, a relatively recent observation, which the University of Birmingham played a leading role in that observation. Exploding massive stars, dying low mass stars, exploding white dwarfs, etc. And here we see two videos of those kinds of processes. Dramatic supernova, where you might have a star blowing itself to bits, and on the right hand side we saw two neutron stars merging, and then finally, again, a massive explosion driving the elements created out into the surrounding space. Now, it's possible to design these very simple videos, but in order to understand in detail what actually goes on inside these processes, very complicated calculations are required. And what I'm going to do is I'm going to show you a calculation which attempts to simulate the formation of the elements inside that merger of neutron stars. Now, there's a lot going on here. This is a simulation by a collaboration called Skynet. What is shown here is all of the elements, so elements increasing Z, and with different neutron numbers, so different isotopes of those elements. Up here, we see the evolution as a function of time of either in blue, the density, in red, the temperature, or in black, the heating rate. And this is time marching along here, and here you can see time here. And then bottom here, we have got the mass abundance, mass fraction, as a function of A over here. It's a bit like the experimental graph that we saw on the last slide. So let me run that simulation again. You can see that as those stars, neutron stars, merge, what happens is you create a whole sweeping set of isotopes way out here, away from stability, and then gradually they radioactively decay back into what's called the valley of stability. These squares here, the stable isotopes, and they're gradually being filled up as those nuclei decay, as time runs by, as temperature and density decrease. And one sees, just like in the experimental data, there's some peaks that appear in that distribution, those peaks in particular regions of this chart. And so this is very strong evidence that actually we know that the elements which we're made of were formed in such exotic processes. But that's quite heavy elements. What about the most lightest of elements? And what about what happened back in the beginning of time with the Big Bang, as it was called, Big Bang fusion, Big Bang nucleosynthesis? So in this diagram, what we've got is the early understanding of how that happened. We take protons and neutrons, and you can fuse a proton with a neutron to make deuterium. If I add another proton over here, then I can get to helium-3, and add another neutron, I can get to helium-4. And similarly, if I was to take a hydrogen-2 deuterium and add a neutron, I can get to tritium. Add a proton, I get to helium-4. Now, there's a whole bunch of isotopes over here. So how are they made? Because if I try now and add a neutron or a proton, those elements are unstable, and hence it's not possible to use them as stepping stones. There's a wonderful contribution from a man called George Gamow, who tried to understand these stepping stone processes. And George had this cartoon, which you can see a big gap, which is the mass 5 elements here. How on earth is it possible inside stars for these heavier elements to be synthesized? And George was not only a gifted nuclear physicist, trying to understand these nuclear synthesis processes, but he also tried to communicate his understanding to the public. He wrote this wonderful book, Mr. Tompkins, which is a couple of stories, Mr. Tompkins in Wonderland and Mr. Tompkins Explores the Atom, which tries to bring over science concepts through the world of a bank manager, Mr. Tompkins, and explain quite complicated processes. And here you can see on the front of this car here the fusion of two protons to make deuterium, which happens inside the sun, and George's rocket with his name on it in the Greek alphabet. What the answer is to the conundrum, how are heavier elements formed, that of course takes place in the stars, and particularly the formation of heavier elements takes place in stars such as red giants. And red giant is, or a red giant exists in the constellation of Orion. And what this shows is the main sequence of of stars, and our sun sits here. As during the life cycle of the sun, it will gradually burn all the hydrogen that's available to it, and then slowly, once that energy production through that hydrogen burning is extinguished, then the star will collapse and then reignite helium burning. So in the first cycle, hydrogen is converted to helium, and then that helium starts burning, and the sun will head out on this journey here to become a red giant. And indeed, Betelgeuse sits up here. Now, it was this man here, Fredoyle, a British cosmologist, who really understood what might happen inside a red giant. Inside a red giant, it is possible for two alpha particles, helium-4 nuclei, to join together to make a beryllium-8 nucleus. And that beryllium-8 nucleus lives for a very short amount of time, 10 to the minus 16 of a second. But in that instant, before it decays, it could capture another alpha particle and then form an excited state, what's called the Hoyle state of carbon-12, which then could radiatively decay by emitting gamma rays, decay down to the ground state of carbon. This state, 7.605 MeV, is named after Fredoyle. He predicted it based on the amount of carbon which exists in the universe, and indeed, after his prediction, that state was experimentally discovered. And the intriguing thing is that if you were just to change very slightly the energy of this state, the amount of carbon in the universe would change dramatically. So our existence, the existence of organic life, is very strongly related to exactly the energy of this state. So where does the work of the Birmingham group come in? Well, much of our contribution has been trying to understand why that Hoyle state exists exactly at the right energy and what its structure is. And we now have a very good picture of the structure of carbon-12. Now, there is a very simple equation that carbon-12 is, just as we might predict from that stellar process, can be thought of as 3 alpha particles, and here you can see them rotating. This simple equation over here describes the rotational energy in terms of the angular momentum of this spinning object, J, and a projection of that angular momentum, K, onto the symmetry axis of these 3 alpha particles. So you've got a component K of this rotating object as it spins around this axis, but it could also wobble, so there's other components of spin, and when you add those two together, you get J. And these quantum numbers, 0, 2, and 4, which describe the states in carbon, are these J's. So experimentally, what one sees is a ground state of carbon, which is 0 spin, and then two units of spin, and then 4 units. And that's from rotating around this axis here. If One spins the carbon around the symmetry axis. So now we're looking down on the spin with each alpha particle with 1 unit of angular momentum, 1, 1, 1. That gives a 3 minus state, a 4 minus state, and a 5 minus state. And these are the experimentally known states in carbon-12. Now the Hoyle state, and this is the work where the work of the Birmingham group comes in, we now know to have something like a structure which looks like this. So 3 alpha particles, but the alpha particles are well separated from each other, but rotating to give a 0 plus state, the Hoyle state, 2 plus and 4 plus. So just like the other 0, 2 and 4. The Birmingham group have discovered this state, and indeed discovered this 4 minus state here. And now we have this fingerprint which describes the structure of carbon-12. Many of the measurements that we do and have done have been done on our own accelerator, which is at the University of Birmingham. It's a cyclotron. A cyclotron is an accelerator in which it accelerates particles by getting them to go round in circles, and as you put more energy into those particles, they go into bigger and bigger circles, and eventually at high energy they get extracted along this beamline here. So this is the cyclotron. Here's the beamline, which is under vacuum, and over here you can see some magnets which are used to steer and shape the nature of the beam. The beam then goes off along this beamline here, and we collide particles together to try and understand the structure of those nuclei. And as a student, you would either as an undergraduate, you would have a chance to use this accelerator on a final year project, or as a PhD student in our department working in both instances in our research group. We do a lot of things, so understanding the synthesis of elements in the stars is certainly one of them. We also understand the structure of many light nuclei, and our work has led to an understanding that some nuclei behave as molecules. This is an illustration of the nucleus beryllium-11, where the 2 alpha particles here are orbited by 3 neutrons. And those neutrons are exchanged covalently, just like electrons are exchanged between centers in a molecule. These neutrons are exchanged to bind these 2 alpha particles together. Really exciting and a real challenge to nuclear theory.